would be the last lecture in our series of lectures that we had on explosion and safety. It'll be on quantification of damages as is shown in this slide. And what I show is, we have already learned about different aspects, like we looked at the different explosions. And in the last lecture, that is lecture 35, we homogenized or brought together all the different types of explosions into something known as equivalence or TNT equivalence of explosions. Therefore, we have done this subject considering confined and unconfined explosions, that is explosions within a rigid boundary. We also looked at explosions occurring freely in nature, that is freely in open. We distinguished between confined explosions and unconfined explosions and the type of damage which they could cause. But we have not really quantified the damages which these explosions cause. This is point one. We also looked at different explosions. We said food grains, like at home, we grind sugar. The sugar which we grind for making or for maybe putting on a cake or something like that could also explode. Dust could explode. Similarly, gaseous mixtures could explode. We looked at different explosions involving dust mixtures, gaseous mixtures. We also looked at solid explosives, liquid explosives, and their characteristics of how they detonate and how they burn and how they could generate blast waves. We looked at this. We also looked at something unique in the sense we said, even without chemical reactions, we could have something known as physical explosions, like water could be an explosive under certain conditions. We also looked at cryogenic tanks which explode. We looked at pressure vessels which burst and cause an explosion and cause injuries. Now, having looked at all these explosions and characterized these explosions, it's time that in this last lecture, we look at how to quantify the damages which the explosions cause. You will recall that we said all explosions cause damages. They could be fatal, they could cause injury, they could damage a building, they could damage anything around, an object could be damaged. And therefore, in this last lecture, let us take a look at how to quantify the damages in an explosion. To be able to do so, let us again go back and revisit what we learned. When in an explosion, we said energy is released rather rapidly. You have a very rapid release of energy, and this rapid release in energy causes the overpressure or causes a blast wave or a shock wave. The shock wave decays with distance. That means a decaying shock is what we call as a blast wave. And the blast wave is associated with a jump in pressure, which we call as overpressure. And also, because of the way, since it decays, we found that it is associated with a wind or a blast of wind, which creates a change of momentum and an impulse. And it is this overpressure and impulse from an explosion which essentially cause damages. Therefore, the damages are associated essentially with overpressure and impulse from an explosion. We also found that fragments, missiles, also travel at high speeds from the area of the explosion. They drag objects into the explosion, and these could impact the objects, the buildings, and people and contribute to damage. Not only is a blast wave which causes damage from an explosion, but we have fire which precedes an explosion, which follows an explosion, and fire is always dangerous, and this fire could also cause damage. Not only fire, you are burning substances. We found that most of the solid explosives and liquid explosives are fuel rich. The burning is incomplete. You generate pollutant gases, and these pollutant gases would also harm the environment. Therefore, the question is, how do we put all these things together and quantify what are the destructive effects of an explosion, and that is what we want to do today. Having set our goal, let us also remember that while studying the subject, we know these are the attributes of an explosion, and while doing so, we learned how to prevent an explosion. That means you could inert it, you could make sure an explosion does not take place under certain conditions, and you make those conditions necessary to avoid an explosion. But it is not always possible to avoid an explosion. We have to live with some explosions, and they do cause damage to humans, the living organisms around, they damage the buildings, and also the objects around. Therefore, in today's lecture, we will address the issue of damage, though we know how to predict the causatives or parameters of an explosion and how to mitigate an explosion, but we will specifically address the point of how to quantify the damage caused by an explosion. Therefore, let's get started with this lecture, the last lecture in your series, and we get back to understand with a specific example. Let me start with an example. We said in an explosion, you generate a blast wave. The blast wave has an overpressure. And by experience, by measurements, we know that when the overpressure is around 0.7 kPa, that means less than, let's say, less than maybe 1/100th of an atmosphere, the window glass panes break. That means if you generate an explosion which causes a blast wave to have an overpressure of 0.7 kPa, the window glass panes break. We discussed this in lectures 5 and 6. Similarly, if you have the eardrum, we hear because we have a eardrum which vibrates when some sound is incident on it. At 34 kPa overpressure, the eardrum ruptures. And similarly, when we have a brick building, when you have an overpressure of the blast wave generated by the explosion of 55 kPa, the brick buildings get damaged. If the overpressure is higher than 55, let's say of the order of 70 kPa, a person who is standing or who is walking gets knocked down because of the compression of the overpressure. He gets knocked down. Not only does he get knocked down, the wind effect, namely the impulse from an explosion, drags him and causes damage to him. Therefore, similarly, if the overpressures are much higher, I go directly to a somewhat higher value of overpressure of 2 atmospheres. What happens is at 2 atmospheres, if a blast wave were to hit us, our lungs will get damaged. And if the overpressure is of the order of 7 atmospheres, well, it is lethal. We cannot survive. We will be dead. Therefore, we find that yes, one way of quantifying the damages is by looking at the overpressure of blast wave generated. But then it's not so straightforward. We say, well, at 34 kPa, if there is a blast wave from an explosion, it will cause our eardrum to rupture. But it's not always so. Let's take an example. Let's take an example of a little infant, a baby. The eardrum is not fully developed. The infant is very fragile, and therefore instead of 34 kPa at which the eardrum will rupture and the baby will no longer be able to hear, maybe at 20 or 25 kPa itself, the eardrum will rupture. We could also think in terms of a very strong man, an young man who exercises daily, he is very resistant. For him, instead of 34, even at 60 kPa, if a blast wave were to hit his ear, nothing is going to happen to him. Therefore, what happens is, see, all of us are not equally strong. So also not all buildings are equally strong. Some have good materials of construction, some have little weaker materials of construction. Therefore, some of the objects or some of the humans are more vulnerable to damage than the others. Therefore, now we have added one more dimension. We said, even though earlier we said that at an overpressure of 0.7 kPa, window glass pane will break. Not all glass panes will break at 0.7 kPa. Some may break at 0.6, some may not break at even 10 kPa. Therefore, there is a range over which it will break. And therefore, to quantify the damages, we have to be a little more clear because some are more vulnerable than others regarding the damage. Therefore, we find if we talk of a mean value of 34 kPa at which the eardrum sort of ruptures, there is a band, and this band depends on the vulnerability of people or vulnerability of buildings or vulnerability of objects to being damaged. Therefore, in addition to the mean, there is a range or variance above the mean at which damage to building can take place. And it is necessary for us to include this variance. If at all, we have to quantify the damage. It's not that I say 34 kPa. If I have a blast wave which is generated by an explosion, maybe our eardrum will go. No, it is quite possible at 20 it could happen, it could be at 60. Therefore, how do we incorporate this is the question. Therefore, we immediately tell, yes, I have learned about this in my subject of statistics or probability, which we studied in the high school final year. And we know that, yes, probability, standard probability distribution consists of a mean. About the mean, we could have some changes, that is variance about the mean at which the changes could take place. That means there is a dispersion, and this dispersion about the mean is characterized by standard deviation. And standard deviation, we know, is equal to the value minus the mean whole square divided by the number of observations minus 1 under root, that is the standard deviation. Therefore, there is always a dispersion about the mean, and we need to take into consideration this particular dispersion into account while characterizing the damage or quantifying the damage from an explosion. Therefore, now we say, well, I'm leaving all whatever I have studied in explosions, getting back to a probability distribution, getting back to the question of standard deviation. But is it right to do so? Let's again take a look at the problem to make sure we are clear about it. We said, well, the damage is caused by overpressure. In some cases, when the overpressure is of the order of 70 kPa, a man gets knocked down. And when he is knocked down, the impulse or the change of momentum drags him along the road or along and causes further damage to him. Therefore, it's not one parameter which causes the damage. It is overpressure plus impulse. It is further complicating the story. Therefore, when we talk of eardrum rupture, since the eardrum is fragile and it is very thin, there is no room for impulse. The overpressure itself causes the damage by spall, and the impulse does not have any possibility of causing further damage. Similarly, if I say, well, there is a fire preceding an explosion, or there is a fireball which takes place after an explosion, we know high heat is radiated from the fire, and well, this heat could also cause some injury or burns to the people, or it could also cause death, heat radiation be if it is intense. Therefore, intensity of a radiation is important. But if people in our country, they even walk barefoot on the fire. And you have people who take in kerosene oil, gurgle it in their mouth and spit out fire. He does not get hurt by the fire. What is the trick? Well, the man who treads over fire, he walks so fast that the residence time of his foot on the hot fire is almost negligibly small. There is no time for heat to get transferred. Similarly here, the man spits out fire, but make sure that while spitting out, the fire is at some distance from him, and therefore the heat radiation from the fire is not able to harm him. Therefore, whenever we talk of fire, it is not the radiation alone, it is the distance and also the time over which the radiation takes place, and therefore it is not a single event like radiation which causes the problem in the case of a fire, but it is the heat radiation into the time which causes the problem. Therefore, the duration of a fireball in case of an explosion is also important, and therefore the parameter which causes damage is not only the heat radiation, but it is the intensity of heat radiation into the tank, and therefore we say it's not a parameter like an overpressure, impulse, or heat radiation which causes the damage, but there is something like an effective parameter which could be a product of the parameters. So we are confusing the issue. Instead of starting with overpressure, which causes the damage, we say, well, overpressure and impulse can cause a damage. Instead of talking in terms of a fire from an explosion, which can cause heat radiation, we say, well, time can also cause an explosion, cause the damage. And in addition, if you look at pollutants from, let's say, an incomplete combustion, we have carbon monoxide, which is an incomplete product of combustion. And when we inhale carbon monoxide, what happens is the hemoglobin in our blood, it gets affected, and it takes some time because human beings' response time is important. And therefore, unless the carbon monoxide is present for a certain time period, well, it does not affect us. Therefore, it's not the concentration of the pollutant which is important, but the time over which the pollutant is there is important, and therefore the effective parameter becomes concentration into time. Therefore, we say, well, the effective parameter is something which is more important rather than a single parameter, though in practice, for hemorrhage of the brains, the overpressure is important. For eardrum rupture, the overpressure is important. For injury from impact, well, the overpressure and impulse is also important. For glass breakage, generally, overpressure is only important, but the direction in which the splinters of glass are thrown out depends on the impulse, and therefore, impulse and overpressure do play a role, and therefore, we talk in terms of an effective parameter. So also, when we talk in terms of the pollutants causing damage, we say fatality from carbon monoxide generated depends not only on the concentration, but concentration into time. But if we talk in terms of an ammonia gas which is getting generated, ammonia is much more corrosive and much more dangerous than carbon monoxide. Therefore, the concentration tends to be more important. Therefore, if we talk in terms of damage from ammonia gas, it is concentration squared into T. Therefore, instead of talking in terms of a parameter from an explosion like overpressure, the heat radiation, maybe the impulse, we have to talk in terms of a combination of parameters, which becomes an effective parameter. And in case of a fire, we said time is important, therefore it is a product of intensity of heat radiation, and when people model it, they found that it is intensity of heat radiation to the power 4 by 3 into the time in seconds divided by 10 to the power 4, which becomes an effective parameter. Therefore, now we say, well, instead of talking in terms of the damage being caused by a single parameter of a blast wave or a single parameter of an explosion like a fire, maybe a pollutant from a fire, we have to necessarily talk in terms of an effective parameter. Therefore, let us now take a look at this effective parameter and what it is. The effective parameter is what we call as a dose. All of us have heard the term dose. You go to a doctor when you are not feeling well. He says, well, you take 2 of these particular tablets, your fever will go. Or he gives you a little bit of liquid potion and he says, drink half a ml or 1 ml, a small quantity of it. That quantity is what we call as a dose, maybe 2 tablets to prevent a fever in your body. Therefore, this is what we call as a dose. And similarly, the effective parameter or the thing which causes the damage is also known as a dose. Therefore, dose causes the damage or the adverse influence rather than a single parameter from the explosion, and the degree of damage depends on the dose, namely the effective parameter. I will again repeat by saying the effective parameter is what we call a dose, and this dose is responsible to cause harm. Therefore, the degree of damage will increase as the dosage increases. Now, you go to a doctor, he specifies you take 2 of these strepsils or 2 of this particular uh, paracetamol to subside your fever. You come home, instead of taking 2, you take 100 of these tablets. Well, it's not going to be so. It's going to cause harm. Therefore, the dose, if taken in large quantities, just like in an explosion, will cause harm. In fact, there was this very famous scientist. He lived something like 1600 years ago. His name was Paracelsus. He made a beautiful statement. He said, dose alone makes a poison. All substances are poisonous. Even water is poisonous. There is nothing in life or nothing in nature which is not a poison. It is the right dose which distinguishes a poison from a remedy. Like, for instance, as an example, you drink water in controlled quantities. If you were to drink lots and lots of water, or you go into a swimming pool and you get drowned in water, therefore, for large quantities, well, it becomes a poison, it becomes deadly. And therefore, it is this dose which is the effective parameter of an explosion which causes the damage. Having said that, let us go back and examine what this dose can do. And therefore, instead of a single parameter like overpressure, a single parameter like impulse, a single parameter like we say heat radiation from a fire or the pollutant, we take a look at the dose, which we also call as a stimulus. As the stimulus increases, well, the damage caused is more. We talk in terms of damage caused by the dose, and we just now said some people are more vulnerable to damage than others. Therefore, instead of a single value of the dose, well, there is a range of values of a dose over which the damage is caused. Therefore, our main aim to quantify damages is to look at the variance above the mean, to look at the effect of dose on the failure, and can we really come out with a solution to quantify the damages. And this is what we will be doing in this particular class. I hope by now we are very clear about what we said about parameters or the destructive parameters in an explosion. A combination is what leads to an effective parameter called dose. And because some people are more vulnerable to damage than others, well, we need to look at variance in to be able to model the quantification of damages. Having said that, we again go back and take a look at the standard probability distribution. We said, well, whenever we talk of a bell shape. About the mean, well, things keep changing. Some people get affected at very low values of the stimulus or dose. Some people get affected at high values. There is some variance about the mean, and the probability of the people getting affected or the probability of a damage to a building about depending on the dose is on 1 over under root 2 pi sigma e to the power the dose minus the mean value of the dose divided by the standard deviation squared. This is what we learned in our probability. Therefore, we have to look at this particular figure of probability with respect to the dose, and here the dose or stimulus is marked by x, mu is the mean value, px is the probability. Therefore, let's take a look at this. Let's try to see whether we are able to predict something nice. Therefore, we said, well, the probability depends on 1 over under root 2 pi sigma e to the power minus x minus mu divided by sigma square. And we know that the total area under the probability distribution curve is equal to 1. We know this. And we also said, well, the standard deviation depends on the degree to which there is variance above the mean value. Therefore, can we have some more better understanding of the standard deviation and the probability, since we have not been using it in our earlier uh, lectures. Therefore, let us just take a look at this and make sure we are clear about it. Supposing we say that we have a particular case of an explosion wherein the dose X is very, very large. If the dose X is very, very large, well, the buildings are damaged, people die, nobody can escape, and therefore the variance or the standard deviation above the mean is a small number. Whereas if the explosion is of low intensity, well, some people get affected, some people get affected, some people do not get affected. You have a large value of standard deviation. Therefore, the standard deviation, which we denote by sigma, seems to be a good point. That means standard deviation varies depending on the parameters of the explosive and also the health of the object. But if the amount of the dosage or the effective parameter is very large, well, the standard deviation would be small. Therefore, with this physical attributes, we can go back and try to understand more about standard deviation. What do we say standard deviation? Well, this is the probability distribution. Well, you say 1 sigma, 2 sigma, 3 sigma. What does it represent? Well, one standard deviation is between minus sigma to sigma of the probability distribution, and the area of the curve under one between minus sigma to plus sigma is something like 68.3. Similarly, if I take instead of minus sigma, I multiply it by 2, I add more area under the curve, then between minus 2 sigma and plus 2 sigma, the area under this curve gets enhanced by 13.59 plus 13.59. Therefore, the area between minus 2 sigma and plus 2 sigma of the probability distribution curve, mind you, the total area is 1, is now becomes 95.44%. If I go to 3 sigma, well, I add another sigma here. It becomes 2.14%, 2.14%, and the area between minus 3 sigma to plus 3 sigma becomes 99.7%. Therefore, the standard deviation is able to tell us something much more in terms of finding a point within the probability distribution curve which can cause the damage. Therefore, let's again take a look at it. We tell ourselves the area between minus sigma to plus sigma is 68.3%. Between minus 2 sigma to plus 2 sigma, it is 95.4%. Between minus 3 sigma to plus 3 sigma, it is something like 99.7%. If I talk in terms of minus 4 sigma to plus 4 sigma, it's almost like 99.999%. If I talk in terms of minus 5 sigma to plus 5 sigma, it's almost 1. It's almost the total area under this curve. Therefore, we find, yes, there is something very important message to be had from standard deviation. Now, to be able to go forward, we again go back and say, well, there is stimulus or dose X, and depending on the stimulus, the probability distribution is something like this. On an average, on an average, mu, maybe this number of people get affected, but some people are more vulnerable, they get affected here. Some people are strong, they get affected here. You have a probability distribution. Now, instead of a dosage being average value mu, let us consider a small value of dosage X. Then what is going to happen? Maybe the number of people who are going to get affected is going to be the area under this particular curve. If the dosage is X over here, the number of people are going to be affected by this particular area. If the dosage is very high, well, almost all the people, 100% of the people are getting affected. Therefore, the area under the probability distribution curve up to the particular area of the dosage will be a good indication of the response or the number of people getting affected. Therefore, let's go back and again make sure we have understood it. We find that above the mean value, I have certain deviations. If the dosage is low, the deviation is larger. If the dosage is high, well, the deviation is smaller. Now, for a given damage, the response or the number of people who get affected depends on the area under this particular curve. And what is the area under a particular curve? We looked at it earlier, looking at the area under between minus sigma to plus sigma, between minus 2 sigma to plus 2 sigma, and others. And therefore, we say, well, the area under the curve is something what we call as a cumulative distribution, cumulative value of the distribution. And cumulative distribution is denoted by phi x, and it is equal to minus infinity to the particular value of x of this particular curve integrated between minus infinity to x, or rather phi x is equal to minus infinity to a particular dosage x, px is the formula for this curve, into dx, and therefore phi x is equal to minus 1 over 2 pi into sigma outside into minus infinity to dosage x e to the power minus x minus mu squared divided by sigma squared. And therefore phi x, which is a cumulative distribution, is going to tell you what is the response of people, or the number of people who get affected, or number of buildings which get affected. And this is how we should be really quantifying an explosion, the damage from an explosion. Therefore, we tell ourselves we are more interested in cumulative response, or rather, we have the dosage, we look at the cumulative response. Now I say, well, cumulative response is something which we call as a response. And now this is the probability distribution. If I have up to x, well, the curve is increasing. The curve goes from here to here. If it goes here, it's more steeper. If it is in this droop, it droops off. And therefore, the response versus dose is a shape, something like a figure sigma. Sigma, the Greek letter sigma. It looks like something like a sigmoid shape. And now, if I want to stretch the value here, if I want to stretch the value at low values, and if I want to compact the response at high values, instead of plotting dose, I can as well plot log dose, and therefore the response curves are normally plotted as cumulative distribution versus the log dosage. Therefore, you have dose response curves, and these dose response curves are very important, not only in explosions, damage from explosions, but a doctor or in the clinics, they use dose response curves to be able to find out how people behave. Like for instance, recently we had this pandemic, corona, which is causing a lot of problems. People find out what is the response to a particular dosage, particular vaccine, and find out what is the dose response curves. And therefore, these dose response curves are important in all these subjects with which we deal with. And therefore, the response is nothing but the cumulative distribution, which is minus infinity to the particular x of the probability distribution into dx, or 1 over 2 pi, or sigma should have been outside, minus infinity to the dosage e to the power x minus mu whole squared by sigma squared, which is where sigma is the standard distribution. See, we don't want to get into other fields. We are interested in quantifying the damage from explosions. Therefore, we are basically interested in the response, and therefore, or rather response, or I can also say we are interested in the cumulative distribution, phi x. Therefore, let's take a look at this. Therefore, we say, well, we talk in terms of dose response curves. And what is a typical dose response curve? It is a sigmoid shaped curve wherein response, namely cumulative response versus dose is plotted. It is in the shape of a sigmoid. And this is what we want to be able to find out, quantify the disturbance or quantify the effects of an explosion. Therefore, let's go forward. Therefore, we say dose response curves are important. They quantify damages from explosion. It is influenced by the level of dosage because the standard deviation depends on the level of dose. If the dose is very high, everything is damaged, the standard deviation is less. We also said that in the medical profession, well, there are acceptable level of dosages. And if the doctor suggests a particular dosage and we sort of don't follow his instructions, we come home and take a lot of drugs, that means we take excess dosages, what happens? It becomes bad, sometimes we get more sick, sometimes we die itself. Therefore, the dosage signifies if the dosage is very high, it can lead to loss of life, destruction of buildings, and when we say loss of life, we say lethal, and the dosage which leads to loss of life is known as lethal dosage. Therefore, lethal dosage is abbreviated as LD, and it happens when the dosage level is high. Like for instance, when we talked in terms of a parameter overpressure, we just said a single parameter overpressure. If the overpressure is greater than 700 kPa, well, nobody can escape, and that dose becomes lethal. Therefore, we say it is a lethal dose. Similarly, let's plot this. Now we know how to plot the response versus the dosage curve. Therefore, we say, well, we talk in terms of effective dose, which is the dose. We said it's better to plot it in terms of log scale such that we stretch out the points which are low dosage and compact the points which are high dosage in the logarithm curve. And therefore, we say, well, for lethal dosage, that when the dosage is high, this particular curve tells you how many people respond. If the dosage is very high, 100% people die. If the dosage is somewhat smaller, a fewer number of people, very few people to survive. This particular curve is very steep because it is high dosage with small standard deviation. But we can also talk in terms of dosage, wherein we talk in terms of an effective dose. What is an effective dose? Well, I'm standing here, there's some explosion, it comes and hits me. Well, I get hurt, I get a fracture, but then this fracture I can go to a doctor and the doctor will set it right. Maybe after 2 months I become all right. That means the injury which I suffer is no longer lethal, but it is reversible. Such reversible failure is what is known as an effective dose, or an effective dose causes a damage which can be reversed. Therefore, maybe injuries which can be treated and in which people become all right is known as an effective dose. Therefore, you find that for effective dosage, well, it takes a longer time because the standard deviation is larger, and in between 100% and 50 and 0%, we have 50% of the people who are there. This dosage corresponding to 50% of the people responding is known as ED50. Similarly, recently when you had this pandemic, corona, what happened? Maybe some people, the dosage was given, you find out whether 50% of the people get affected, 80% of the people get affected. People say this particular vaccine is more suited than the other, and this is how we talk in terms of effective dosages. Therefore, effective dosage is something which is reversible, and in between the effective dosage and lethal dosage, we have another dosage which is known as a toxic dose. Toxic dose is one in which the injury or the damage caused is not totally reversible. Like for instance, in an explosion, somebody loses a finger. Well, the finger is lost. It is not reversible. It cannot be put back. Therefore, it becomes an irreversible injury, and therefore, the toxic dosage is between the effective dosage and the lethal dosage. Therefore, we find that for lethal dosages, well, the standard deviation is narrower, the response curve, that is the cumulative response curve versus the log dosage curve, is very steep. For the toxic dosage curve, it's a little shallower. For the effective dosage curve, it's more shallower. And therefore, we have to use these curves or the response or the dose response curves to be able to quantify the explosions. Let's see how to do that. Let's therefore go forward. We have talked of three things so far. One is we talked in terms of probability distribution and cumulative distribution. The cumulative distribution we said is the response, cumulative distribution phi of the dosage. We also talked in terms of standard deviation. Now the question is, can I put all the things together and have a method of quantifying? First of all, we recognize that, well, the standard deviation, sigma, is along the dose axis. It is along the x-axis, that is along the stimulus or the dose axis, point 1. Point 2, the response is sigmoid shape. This sigmoid shape is steeper when the standard deviation is smaller, is more. That means it is a little more flat when the standard deviation is larger. Therefore, can we put this or of the standard deviation, the dose, and the shape together and arrive quantitatively how to take a look at the quantifying of damages. Therefore, we summarize what little we have been able to understand so far together. We said dose response curves are curves which define the cumulative response versus the dosage and depend on the variance, that is the standard deviation, point 1. Point 2, standard deviation is along the dose axis plotted in terms of log dose. And why did we plot as function of log? We wanted to, to elongate the low numbers which are important and compress the high numbers which are not that important. Therefore, we plotted the log dose. And third, as dosage increases, the response or the number of people who get affected or the cumulative uh, probability distribution increases or the damage increases. Therefore, as we increase the dosage, we move from effective dose to toxic dose to lethal dose. And now we have to put things together. And that's all what we have to do to be able to quantify an explosion. Therefore, let's now do it. It's quite simple. Now I put some numbers in front of you. We talked in terms of cumulative distribution phi x, which is nothing but response. We talked in terms of standard deviation sigma. What did we say? The, the area under the probability distribution curve between minus sigma to plus sigma, we said is some value, 68.4%, 0.684. Between minus 3 sigma to plus 3 sigma, it is something like 0.99, 0.97. Therefore, if I'm interested in the area or the cumulative distribution from minus infinity to, let us say, minus 3 sigma, that means the area, that is a cumulative distribution when x is equal to minus 3 sigma. What is this value? What is this value of this curve here? Well, the area of the curve from minus 3 sigma to plus 3 sigma is something like 0.997. And therefore, the area under this curve here and this area curve here put together is equal to 1 minus 0.997. And the area here is equal to half of 1 minus 0.997, which is equal to 0.0016. Therefore, the cumulative distribution up to minus 3 sigma, that means phi of minus 3 sigma, is equal to 0.0016. This is important, and therefore let me put two more figures for you. Let me again revise it. You said that the probability distribution curve is given by 1 over 2 pi sigma exponential of minus x squared by 2 sigma squared. The area under the probability distribution curve is 1. Now, if you look at the area under the probability distribution curve between, let us say, now let us consider 2 sigma. From minus 2 sigma to plus 2 sigma, we said it is 95.4%, that is 0.954 of unity. And therefore, phi x corresponding to minus 2 sigma, that is the area of the curve, that is phi x up to here, the cumulative distribution, phi of minus 2 sigma is equal to, now we need this particular area. Therefore, what I do is I consider the area over here. I know that the area from here to, from middle over here to here is 0.5. I know what is the area under this curve. This is equal to 0.954 divided by 2, and therefore I get the value as equal to 0.0036. Similarly, if I consider a high dosage value of plus 3 sigma, somewhere over here, what is the area under this particular curve phi x? it is equal to this 0.5 plus the area here plus the area here plus the area here. It is equal to effectively what I have to subtract out this particular area, which we found out is equal to 0.0016 or 15, and therefore it's equal to something like the total area is 0.9984. Therefore, if I were to plot a response curve, I would have got for minus 3 sigma as 0.0016, for plus 3 sigma as 0.9984, for minus 2 sigma as 0.036. Therefore, for any value of standard deviation, we can get the response. Therefore, it becomes necessary for us to determine the value of the standard probability, standard deviation. Let us try to now put a value on how to quantify this difference. This is what we wanted to do. Therefore, let us now define something new. It's not really new. All of us, in our first year and second year of engineering, we talk in terms of Fourier transform, Laplace transform. And what is it we do? We take time signal, make it into, let's say, a Fourier transform or Laplace transform, we transform it, and we take the inverse of the Laplace transform and get back the original number. So also, when I talk in terms of a cumulative distribution phi x, and now, instead of taking the cumulative function, I take the inverse of the cumulative function. That means cumulative function is phi x. I take the inverse of the cumulative function, phi inverse of phi x. What is it I get? I get x. Therefore, we talk in terms of inverse of cumulative distribution function as being phi inverse of phi x giving back x. And therefore, now I go back and say, yes, I found out that the cumulative function of minus 3 sigma is equal to 0.0016. Therefore, if I take the inverse of this cumulative function 0.0016 gives me back the value minus 3 sigma, and therefore the inverse of the cumulative function of minus 3 sigma gives me back minus 3 sigma. The inverse of the cumulative function of plus 3 sigma, which is equal to inverse of 0.9984, gives me the value of plus 3 sigma, or the inverse of the cumulative function minus 2 sigma gives me back the value of the standard deviation minus 2 sigma itself. Rather, we tell ourselves, if I take the inverse of the cumulative distribution function, I get back the standard deviation itself. And therefore, if I take now, instead of minus 2 sigma, I take minus 5 sigma, I found that minus 5 sigma is almost the area under this curve. Between minus 5 sigma to plus 5 sigma is the total area under the probability distribution curve. And therefore, phi inverse of phi of minus 5 sigma is essentially equal to 0, or I get the inverse cumulative distribution of 0 is equal to phi sigma, or cumulative function of minus 5 sigma is equal to 0. Let's try to use this to be able to quantify the damages. Therefore, we say, well, we talked in terms of a cumulative distribution, and to ensure that all of us are on the right track, we talked in terms of a cumulative distribution function phi x as equal to between minus infinity to the dosage of the probability distribution of dosage into d of the dosage, or minus infinity to x of px dx, which is same. Since minus infinity is same as minus 5 sigma, I can write it as minus 5 sigma to the value of x, which I'm interested. Well, x is the dosage or the stimulus, px of dx. And I also know that phi of cumulative distribution of minus 5 sigma is equal to 0. Therefore, I would like to use the cumulative distribution function and the inverse, since we have phi inverse of phi x is equal to x. That means x is the dosage. I get back the dosage, and this can be used to be able to quantify a disturbance. Let's try to do that. And to be able to do that, we use something known as probability unit. Px is the probability function. We said phi x is equal to minus infinity to x of px dx. which is equal to minus 5 sigma to x of px dx. The inverse of the cumulative distribution function is known as the probit or the probability unit. We define probit, a term known as probit, which is known as a probability unit, as the inverse of the cumulative distribution. Rather, we have phi inverse of phi x is equal to y, where y is known as a probit or probability unit. But phi inverse of phi x is equal to x, therefore y is equal to x, and therefore the probit becomes equal to the dosage itself, where the cumulative function is equal to minus phi sigma to the particular value of probit into or x or y of px dx. Therefore, probit, what we define, is the length scale along the dose axis. This particular definition of probit is important for us to be able to understand, and therefore let me repeat again. Whenever we say the inverse of the cumulative distribution is equal to x, the inverse of the cumulative distribution is what we call as a probit. Therefore, the probit gives you the value of the dosage along the x-axis. Having said that, let's try to put it together. We'll do a simple problem such that we can internalize it. Therefore, when we talk of response, we are talking of the cumulative distribution. We talk of cumulative distribution being from minus 5 sigma to the particular value of x, which is from probit, we say is equal to y of px dx. And this particular curve we said is sigmoid shape. A sigmoid shape is rather difficult to use. Nowadays with computers, it's not that difficult, but it will be much easier if we could linearize the curve such that we can readily do the problem. Therefore, instead of using the cumulative distribution, we saw if I take phi inverse of phi x, I get x, and which is probit. If I plot the response curve phi x, that means you will recall we plotted phi x as a function of the log of the dosage. Instead of plotting the response curve instead of the log dosage curve, I plot now the response as a function of the probit y. The curve is not so much sigmoid, it becomes a much more linear. Therefore, a plot of r versus phi x, where x is the dosage, is sigmoid, r versus probit is relatively more linear and much more easier to interpolate. Let's see this. Here, y is the probit, r is the response curve. Instead of plotting the value of response as a function of dosage, I plot it as a function of probit. The curve is a little more linear, and therefore I can always say the response or the cumulative function is a straight line, A of probit and B, and therefore the moment I know y, the probit of an explosion, I can find out the number of people who died, the amount of damage which is caused, and therefore I can get rid of the shape of the sigmoid shape in the dose response curve. In fact, the dose response curve is something like this. If I plot against y, it is a little more linear. I can use the straight line. I have the response as equal to r is equal to ay plus b. But then how do I determine probit? I need to determine the value of probit to determine how many people die, how many people get reversible injury, how many people get toxic injury, how many buildings are getting knocked down. Therefore, I need the value of y. And therefore, to be able to get the value of y, I again revisit what little we have done so far. We talked in terms of a probit y, and how did we define it? We say response or the cumulative distribution goes from minus infinity. Minus infinity, we said, is almost same as minus 5 sigma, to the value of probit divided by 1 over 2 pi into sigma is outside, e to the power minus x squared by 2 sigma squared dx. And therefore, now, for a minimum dosage, threshold value of dosage d0, before this no harm is done at all. The dosage is so insignificant that there is no effect. Therefore, I can substitute minus infinity by the threshold value of dosage at which the harm gets done. And since the axis is log dosage, I show it by ln D0. And the upper value, I'm interested at this dosage, I'm interested at this dosage, it is ln D of e to the power. I put it as a dummy variable u instead of x squared by 2 sigma squared. I show it by this dummy variable. And this response can be written as ay plus b. Therefore, the response linearly, I show it as ay plus b, and I show the value of ln here, the value of ln here, threshold value, the dose which you are interested, ln d. And therefore, when I look at this curve, I look at this particular value, I immediately tell myself, well, y minus 5 sigma is equal to ln d minus ln d0, and therefore the probit y is equal to ln d minus ln 0 plus 5 sigma. Now ln d0 for a particular injury, maybe a fatal injury or a particular building getting knocked down, is a standard, and therefore it is a constant. Phi sigma is a constant, therefore it can be added together to as a one parameter k1, which is a constant for a given damage. Ln d, I put another k2 here such that it takes care of any other deviation, and therefore I can write the probit y as equal to k1 plus k2d. And once I know the value of the probit y, I can calculate r is equal to ay plus b, wherein I know the value of a and b, namely, I say, well, this is a linear curve, the values a and b is known. Once I know y, I can find out the response of the people who are affected. Therefore, for a given dosage d, the response R can be determined, and here K1 and K2 are known as probit parameters. The value of K1 and K2 are determined for different explosions. The different parameters of the explosion are put together in terms of an effective parameter, D, dose, and K1 and K2 are made available. As an example, when I talk in terms of probit parameters K1 and K2, for fatality from a flash fire during an explosion, the value of K1 is minus 14.9, K2 is 2.56. This is put together in literature because we know this is the type of damage which takes place. For a person, eardrum to rupture, whether it is an infant, whether it is an old man, whether it is an energetic man, K1 is given by minus 15.6, K2 is given by 1.93. Glass breaking, K1 is given by minus 18.1, K2 is given by 2.79. Similarly, for fatality from a toxic like carbon monoxide, it's given by this value. Therefore, you have K1 and K2 which are specified for different explosions. I can determine the value of Y as equal to K1 plus K2. K1, K2 are known. We know the dosage which is going to be available at a particular site from a damage. We know the dose. I know the value of ln D. I can determine the value of Y. And once the value of Y is known, I can calculate the response or quantify the number of people or number of buildings which get damaged. And this is how we quantify the damages. Let's do a simple problem. But before I do the simple problem, the value of A is 38.2 for the response, and B is 141. This is in R is in percentage. Some people do not like to use a simple formula. They like to use a cubic equation instead of R, and R is equal to, they say, in terms of probit 3.25 y cube plus 48.76 y square minus 206.6 y plus 270.35. But I think, too much of details is not really required. A linear formula is good enough, and this is how we calculate the number, the response to an explosion, and the quantification of damages. To be able to be crystal clear, let's do a simple problem. Let's take an example. Let's take this example of the blast being generated from an explosion to have an average overpressure of 40 kPa at a given location. Determine the percentage of people who would lose their hearing at this location wherein the overpressure is 40 kPa. We have said earlier For to lose hearing, overpressure is adequate. Therefore, the effective parameter is overpressure. The overpressure at the particular building or the particular gathering wherein the overpressure is 40 kPa, we want to determine the number of people who are getting affected or quantify the response of the people. The values of K1 and K2 for loss of hearing, K1 we just now saw was equal to minus 15.6, K2 is equal to plus 1.93. The dosage D is specified in the probit equation in terms of Newton per meter square. Therefore, 40 kPa becomes 40 into 10 to the power 3 Newton per meter square. Therefore, we get the probit as equal to K1 minus 15.6 plus K2, which is 1.93, ln of y is equal to ln of d is equal to 40 into 10 to the power 3, that is 40,000. Therefore, the probit y is equal to minus 15.6 plus 1.3 ln of 40,000, which is equal to 4.85. But y is equal to K1 plus K2d, we are able to determine the value of y, and this becomes equal to y, we get the value of y. But then R is equal to, the response is equal to AY plus B, A is equal to 38.2 minus 141, where R is in percentage. We calculate the value of y here, put it into this equation, and we get R is equal to the y, what we determine here is equal to 4.85. We substitute the value of y here, and we get R is equal to 38.2 into 4.85 minus 141, which is equal to 54%. Therefore, we find that 54% of the people at that particular location will become deaf. That means their hearing is lost. And this is how we quantify the damage caused by the explosion. Similarly, we could have a fireball. We could have something like an impulse. We could have combination of impulse. And for each of the problems, or each of the hurt, or each of the injury, we will have the value of K1 and K2. We determine the value of Y. We use the response using the value of the probit. We calculate the value of probit. We calculate the response, and we find out how many or what is the quantification of the damage which takes place. This is how we quantify damages. And to sum up, in this particular last lecture, we used the probability unit, namely probit y, which was equal to inverse cumulative of the cumulative distribution y. We determined the people surroundings adversely affected by explosions. We determine the value of y in terms of probit parameters K1 and K2 and the dose d, that means logarithm of dose at that particular location. We determine y, and from y we use the value of response. From the value of R is equal to AY plus B, we get the response, the percentage of people. We have already seen how to calculate the dosage for overpressure, impulse, fire, bursting, pollution, and all that. We know how to calculate D. We calculate ln D. We express it in correct units and get the value of probit. And this is how we get the value of Y. We get the value of response. And this is how we quantify the amount of destruction in an explosion. Well, this is what I thought is important that we understand ultimately. We studied about explosions, we studied the harmful effects of explosions, and in this last lecture, we tried to put together and see how best we quantify the destructive effects of an explosion. Thank you.